Let's talk about the atomic structure. So here's how you use this video. Throughout this video, there'll be slides that have green highlighted text on them. That's what you should write if you are using this to take a notebook. And throughout, there's also blue text. These are questions that you should consider or you should answer. And throughout this video, there'll be a visual code that shows up on the screen and a verbal code said by myself at some point. And they can be in any order, so pay attention. So let's get started. So how small is an atom? So let's just take a sheet of paper, right? If you take a small strip of paper and you start cutting it in half, the idea is that at a certain point you're going to reach the atom. In fact, that's where the word atom comes from. It comes from the word atomos, meaning uncuttable. At what point do I reach a point at which I cannot cut anymore? So you see here, this is a start. I think it gets to 1, 2, 3, 4, 5, 6, 7, 8 cuts. I would have to cut a sheet of paper in half 31 times to get down to the size of an atom. Atoms are very, very small. If you took a penny and you enlarged it to the size of the United States, a single atom would be the size of about a ping pong ball, about 3 centimeters. A typical human cell contains about 1 trillion atoms, and this one just really shows how small atoms are. If you were to take a grain of salt and you said, I'm going to count every atom in this small grain of salt, you would be counting for 500 years. That's like continuous counting. So let's talk a little bit about the history of the atomic model. So if you're using this, like somewhere in your notebook, you want to make this like timeline. We're going to learn about 6 different people, 6 different models that we have thought about the atom throughout the years. So the first one we're going to talk about is Democritus. So Democritus first proposed the idea of atomos, meaning uncuttable, in the year 400 BCE. Right? So he proposed that atoms are infinite in number, uncreated, eternal, and that all the qualities of an object result from the kind of atoms that compose it. So this is really the first idea that, hey, if we keep cutting down far enough, we're going to reach a point at which we are getting to uncuttable. So if we fast forward quite a few years, right? So we got John Dalton introduced the sphere model in 1803. So we're over 2,000 years later. He proposed that atoms of different elements have different properties like mass. He was the first one to say, well, atoms have different sizes. He also proposed that atoms rearrange during chemical reactions. So I believe he identified the masses of 6 different elements. He was actually able to identify some atoms before the periodic table. He was able to say, hey, based on these properties, this should be one of those elements. And he introduced that sphere model in 1803. Now, if we fast forward a little bit, J.J. Thomson, he discovered the electron. And he introduced the plum pudding model in 1904. So you can see that in 1904, he proposed that matter was positively charged and had these little tiny negatively charged particles spread throughout. Now this was kind of a big deal because, hey, we've got these atoms. He was the one that said, well, what we think of as the atom is actually composed of positive and negative parts. And he said, I've got this positive, plum pudding with little negative charges throughout. Now, Ernest Rutherford discovered the proton, and he did this in 1911, and he introduced the nuclear model. Now, he did this using a very famous experiment called the gold foil experiment. And that brings us to this question, how can we see something too small to see? And that brings us to the gold foil experiment. So what he did was he fired alpha ray particles at a thin gold strip. Now think about aluminum foil, but gold. And he fired these small alpha ray particles. They're just 2 protons, 2 neutrons, so a helium atom without any electrons. Very high energy particles moving. He expected them all to go through, and you can see over here, if the plum pudding model was that model that atoms were, all of those particles would go through. But what he noticed, I think it's 1 in 8,000 ricocheted. And Rutherford famously said it was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. So using this was what first proposed that nuclear model. He discovered that there's a very small, dense, positive charged nucleus at the center, and most of what we think of as an atom is just empty space, right? So like most of them get through, but very few ricochet off that small dense part, and that's really what our great understanding of what we understand as the model of the atom now, as the nuclear model. Now, Niels Bohr comes along, and he did a lot with the electron, right? He introduced the planetary model in 1913. So he advanced the theory that electrons travel in orbits around the nucleus, and the number of electrons in the outer orbits determine the atom's chemical properties, known as the valence electrons, and we'll get to that later. And this is the conventional, it's called the planetary model, but it's also called the Bohr model because he was the one that proposed this. He discovered, he discovered these shells, and this is really what we use to model the atom now, because we know that electrons have, certain energy levels, and we can model them out like this. Now in the 20s, the 1920s, Erwin Schrödinger introduced the quantum model in 1926. So he used the mathematical equations to describe the likelihood of finding an electron in a certain position. He worked a lot with quantum theory, and you've probably heard about Schrödinger's cat. So he basically said, yes, the electrons have these energy shells, and it's just a probability that those electrons are going to be in these shells. So this is like what our understanding right now of the atomic structure, but we use the Bohr model to map them out mostly. But yeah, the atomic model or the quantum model, that's what we're working with now. So let's briefly go over the different parts of the atom. So the proton, the positively charged particle located in the nucleus. It contributes to the mass of the atom, has a mass of 1 atomic mass unit, AMU. The number of protons in an atom's nucleus determines the element's identity, or the atomic number. The number of protons determines the element. Now the neutron. The neutron is a neutral particle with no charge, 0, located in the nucleus. It contributes to the mass. It's the same size of the proton. We just say 1 atomic mass unit, 1 AMU, similar to that proton. Neutrons help stabilize the nucleus by reducing the repulsive forces between those protons. The electromagnetic forces, they're going out. Well, the strong force holds the nucleus together, and the neutron helps out with that. Now, the electron is the negatively charged particle found in the electron cloud. Very small mass, almost negligible compared. So if we said the proton and the neutron have a mass of 1 AMU, the electron has a mass of 1 over 1,836 AMU. Very, very small. They're involved in chemical reactions and bonding. Their arrangements determine an atom's chemical behavior. So the locations. We already sort of talked about this. The nucleus is the center of the atom. It contains the protons and the neutrons. And the electron cloud is the region outside the nucleus where the electrons are likely to be found. Now, what I want you to see about these parts, right, is that the nucleus, like Rutherford showed with the gold foil experiment, makes up most of the atom's mass, but it is extremely dense and small compared to the rest of the atom. The electron cloud, well, it's very large volume, but very small mass because of those electrons. And here's the like if you were to take an atom and you were to expand it to the size of a football stadium, the nucleus would be the size of a marble at the 50-yard line. So like the atom is mostly made up of nothing. Very small, dense, compact nucleus. The electron cloud is on the outside. So now let's talk about how all this plays together when we're rearranging them with the periodic table. And the atomic number is the first thing we need to learn about when we start putting together a periodic table. It's just the number of protons in the nucleus of an atom and determines the identity of the element. So there's 118 elements, and that's how we arrange the periodic table. You can see this picture off to the right, and that number on top, that's the atomic number. Yeah, and that's how we arrange them, right? Left to right, top to bottom, 1, 2, 3, all the way up to 118. You can see here's a larger picture of one of them. This is helium. The atomic number, that is 2 of helium. All helium atoms have 2 protons. If it does not have 2 protons, it is not helium. Now, the mass number is the total number of protons and neutrons in the nucleus of an atom. It gives the approximate mass of a single atom in atomic mass units, or AMU, just the number of protons plus neutrons. It's always going to be a whole number, and it's going to vary in different isotopes of the same element. So we'll get to isotopes a little bit later. So if we put this together, we get the atomic symbol. It's a short way to show important information about an atom. So I would write the sample over here to the right and maybe make a note of this, but you can see for some reason, the bottom left, they use Z as the atomic number. That's the number of protons. The mass number is top, that's represented by A. That's the number of protons plus neutrons, and the charge is located in the top right. So here's how you read this, right? The number of protons is the atomic number of neutrons is the mass number, minus the atomic number, and the number of electrons is the atomic number minus the net charge. So you can see an example down here, magnesium. So the number of protons is 12, right? All magnesium atoms have 12 protons. The neutrons is the mass number, 24 minus 12, that's going to be 12 neutrons, and the charge is going to be 12 minus a positive 2. And just think about it this way, right? Because protons have positive charges, electrons have negative charges, this means I must have 2 more protons than electrons. So let's go ahead and get a little bit of practice here. If I'm looking at these, I should be able to identify how many protons, neutrons, and electrons each element has, or each atom has. So if I'm looking at this one, let's do lithium, right? So lithium, well, the atomic number is right here. It has 3 protons. The number of neutrons is my mass number, which is right here. 7 minus 3, that's going to be 4 neutrons. Now, this does not have a charge, so that means the number of protons equals the number of electrons. I basically take 3 minus 0, and I get 3 electrons. So let's do a harder one down here, right? So you can see here, you can practice oxygen over here. Now, let's do this one. Let's do chlorine with a charge of -1. So at this time, I'll go ahead and give you that verbal code. It is 897. I say that again, the verbal code is 897. So if I want to find the number of protons, it's right here, the atomic number. It's 17. Okay, well now the number of neutrons is, well, my mass number up here minus the atomic number. I know I've got 35 protons plus neutrons at the center of this atom. I know 17 of them are protons. I take that, 35 minus 17, that is going to be 18. Now, this one is a little bit trickier because now I do have a charge. So if you look here, to find the number of electrons, it is the atomic number, which is, well, 17, and I subtract the charge, which is -1. 17 minus 1, well, remember, if I subtract a negative, I basically add it. 17 minus 1 minus a -1 is 18. And just think about it this way. Don't get too lost in the weeds with the math here. Just say, oh, I've got a -1 charge. That means I have 1 more electron than proton. And you can practice the rest down here. But notice I have another oxygen here, right? Oxygen always has 8 protons. If it doesn't have 8 protons, it is not oxygen. But notice, well, my mass number is a little bit different, right? My mass number is different for those. So let's move on to the next one. Here we go. Valence electrons. Here we go. All right. So valence electrons are the electrons in the outermost energy shell of an atom. The number of valence electrons determines how an atom will interact with other atoms. Elements in the same group or column of a periodic table have the same number of valence electrons. So you can see this atom over here. You can see that it's got 1 valence electron. That's going to determine the chemical properties of this atom. So how about this question here? How did the nuclear bomb help discover painting forgeries? So That brings us to isotopes. We used this a little bit before, but isotopes are atoms of the same element that have the same number of protons but a different number of neutrons. So this means that they have the same atomic number but different mass numbers. Isotopes have similar chemical properties, but they may have different physical properties like stability. So let's use this as an example, carbon. Carbon has three main isotopes, carbon 12, 13, and 14. Those numbers after carbon, those are the mass numbers, because you'll notice they all have 6 protons. All carbon has 6 protons, right? If it does not have 6 protons, it is not carbon. But you notice most carbon is carbon 12, 98.9%, and it has 6 neutrons. Now carbon 13 has 7 neutrons, carbon 14 has 8 neutrons. Carbon 14 is radioactive, and this is the one that we use to carbon date certain old organic matter. So we can tell based on how much carbon 14 is in a certain specimen that if we find a woolly mammoth or something. And this is even used for painting forgeries as well. It decays over time, and we can find out how old it is. You can see I put a map of, or a chart of uranium up here. Most of uranium is uranium-238, but the uranium that went in the atomic bombs needed to be uranium-235. A lot of effort went into isolating uranium-235. Now, like I asked, well, what about painting forgeries? When the atomic bomb went off in 1945, it sent radioactive isotopes all over the world that had not been on Earth before. So all paintings before then, when they were painting without those isotopes. But all the paint after 1945 had those isotopes. So if someone was trying to forge a painting pre-1945, well, the paint would have those radioactive isotopes, and it could easily be determined, oh, this is a fake because it's got these isotopes in it. So that brings us to the last thing that we need to learn about is atomic mass. This differs from the mass number. The atomic mass is the weighted average mass of all the naturally occurring isotopes of an element. It's usually going to be a decimal number on the periodic table. Atomic mass takes into account the mass and relative abundance of each isotope of that element. So this gets into when we start to measure, when we want to mix chemicals and we need to find the mass of the different materials that we're using. But it takes into account the naturally occurring isotopes. So you see here I've got a few examples over here. Silver. Silver is practically a 50-50 split between silver 109 and silver 107. All silver atoms have 47 protons. But if I were to pick one at random, well, it would be about a 50-50 split. So you can see that decimal number down in the bottom left. That is the atomic mass. So you see here it's close to 108 because it's the weighted average for all those isotopes. Look at chlorine over here. Chlorine is about 3/4, 1/4 split. All chlorine atoms have 17 protons, but there's chlorine 37 and chlorine 35, and you can see that the weighted average is going to be closer to chlorine 35 or 35 because, well, I've got more chlorine 35 than chlorine 37. Then you've got carbon, mostly carbon 12. That's why the atomic mass is closer to 12. And then you've got something like mercury that has all these different isotopes all over the place. So once again, as a final thought, there is too much unknown in the universe to take a break from learning. Get out there and question everything.